Okay, next, after we have a successful indexation, like we showed here, we got this accepted orientations.dat file. The next step is to do a fit of the grains. So let's go back to our config file. That's this next section down here. And let's just go through the options that we have. Do fit true. Obviously, if you want it to do the fitting, then this thing has to be true. If it is false, what it says there in the comment is extract grains, it doesn't fit. That means that it goes based on the orientations I gave it and the other options underneath, and it goes and extracts the intensity information around where each reflection should be for that orientation, but it doesn't perform an actual fit. Estimate down here, this can be commented out. Since we're doing something from scratch, I'm just going to comment that out. If you had an estimate in the proper format of a grains file, then you can put it here. When I run this analysis once, by default, it's already made. It's going to make this analysis a subdirectory in the current folder with this name, the analysis name. And it's going to write a file in that directory called grains.out if it's already run it. So I could do a refit based on the previous fit, but if this is commented out, or if it says none, or if it's a file that doesn't exist, then it just goes ahead and says, okay, well, we're just going to do a default fit using the accepted orientations.dat file that the indexation step wrote in the current working directory. mpdiv, this option here, is the number of polar pixel grid subdivisions. What that means is that it's going to draw in 2 theta, eta, and omega regular grid on the image around where each reflection should be. And if I pick 2 there, it knows based on the geometry and the pixel size in angular terms what the size of a Cartesian pixel is, roughly in terms of angles. If you put that as 1, then it more or less picks an angular pixel size that matches locally what the Cartesian pixel size is. If you do 2, that's the first order oversampling, so it takes half the angular pixel size with respect to the Cartesian pixel size. So it's generally good just for extracting the intensities to do a little oversampling. So 2 is the default if you don't, if this is missing or commented out. Panel buffer, this just doesn't, it's a safety thing here. It will not fit things within 10 pixels of the edge of the detector. That's just an expedience for not having windows to look for signal fall off of the detector, where it would grab garbage intensities for the stuff off the detector, NANDs. And then lastly, the threshold here, this threshold can actually be 15, threshold that we were happy with when we were looking at the raw images again here. So tolerances. Now each one of these tolerances, 2 theta, eta, omega, are in a list if you noticed here, because it's going to do a series of fits basically for as many, these all have to be the same length, but these are length 2, these tolerances, so it's going to fit first with the coarse tolerance, then refit based on those results with the finer tolerance. So I'm starting with the pretty sloppy tolerances here. Now the 2 theta and omega, the 2 theta and eta tolerances happen to be total, so not plus or minus. This is the width of the window in the actual angular space. The omega, since it's differently, these are based on the number of whatever you had for interframe spacing, is plus minus instead of a total tolerance. So in this first tolerance fit here, 0.25 degrees in 2 theta, which is huge, 2 degrees in eta, and then effectively 2 degrees in omega because it's plus or minus 1 degree. So this would be plus or minus 4 frames around the reference or calculated angular value that the spot should be in. Of course, these two, you can move around, and the pixels give the pixel size locally gives the discretization in 2 theta and eta on an image. Omega's discretization is based on the step size used in measuring each frame. So they are handled a little bit differently in that sense. If you want to go to this summed image that we have here and actually look at a given spot, let's just take a typical spot here. If you notice here, usually the width in eta and omega are equivalent because those are affected by mosaicity, orientation spread. But if I look on here, again, look at the eta channel here, this spot, if I want to draw a box around it, I'd start at what, 141 here, goes to 142.0, 141.0, so a degree for this particular spot is more than enough to fit the overall size. So giving it 2 in the first step, I can give this 1 degree here so it can get all the tails. And then in the 2 theta direction, which is a radial direction, remember, going out, let's just pick a spot like this guy here. So this is all background around where the actual spot is. But 140.4, 142.8. Yeah, okay, so that's 2 degrees if I want to do all the background. If I'm somewhere in, oops, go back. See if I'm somewhere inside the background here, 156.8 to 158.3. So basically the width of that spot is something close to 2 degrees. The 1 degree spot would be if I'm much closer to the signal here, 157 to 158, 1 degree is probably, I don't want to go much smaller than that to capture enough of the signal. And to eta, you can step through individual frames if you'd like here, but usually 2 theta and eta are relatively equivalent in terms of what these tolerances should be. So remember, this is total range, width of the window, and this is plus or minus number of, it's a plus or minus tolerance, just specifically for omega. You can actually write it in the comment here. Put this up here. Okay. So again, we'll just half the tolerances there. So a wide sloppy one and then the one that's on the peaks. Now the 2 theta tolerance, if I look in here, what's that? 2 theta is 3.65, and up here it's 3.75 roughly, so that's 0.1. To go that small, so I can say 0.1 here. 0.25 is plenty. 0.25 I think is the tolerance I have marked by these lines here, if I am not mistaken. It's 0.3. Okay, so 0.25 is like from here to here. I know that's plenty to carry all my spots. Last but not least, TTH max. Now if I put nothing here, or comment this out, then it's going to load that materials file again like we did for the indexing, and it's only going to use these 5 rings to do the fits. Now that's generally not a lot of data for a single crystal. So either I can do one of 2 things. I can either select manually more rings in here and resave the materials file, or what's usually better is that I can figure out what my maximum 2 theta on the images. So I can go out to one of the corners here. I still have spots you can see going way out into the corners. The 2 theta of, say, this spot right here is 13.9. What's out here? That 2 theta is 14.6. So what I can use here is take all possible G vectors out to, well, 14.75 is what? 14.75 is somewhere around here. So that's in from the edge. it will know, it's smart enough to know what's on the detector and what's not on the detector, so you don't have to worry too much about this. But yeah, if you just put the pixel cursor in the corner, take something that would fit that 2 theta position here, then it will use all available reflections instead of just the ones you selected for doing the indexing. So you can see true, false, or non-negative value. Non-negative value, that's what we have in here. TTH max true just uses the detector instead. It gives you basically the maximum 2 theta that would give you a complete ring on the detector. It's not as important for the single crystal. False is the same as not having it in there at all. That's the default. Oh, sorry, the defaults are true. False just means use whatever you had manually picked in here, which in some cases you need to do if you specifically want to ignore certain reflections, but it's not the case for the calibration. So let me save that file here. Go back to our shell. So our last command we had run was the find orientations command. If I type hexrd again, notice there's a fit grains command under the find orientations. So if I say hexrd fit dash grains -h for help, again, it only takes one positional argument. It's pretty easy. Just like the find orientation commands, all we have to do is give it the configuration file. Then there's a couple of options here. Again, a force, and then there's a clean. The difference between these is that when you do the fit grains, it's going to cache the raw data from your images into a compressed format. If you do -F, it will just overwrite an existing analysis in terms of the log files and the outputs, but it will not overwrite a frame cache if it already exists. The -C is to clean. Not only does it overwrite the existing analysis, but it re-caches the frame. So if you do something like change the threshold here that you want to use, you want to make it higher or lower, then you would want to run this with the clean option, so that it would recache the frames with the new threshold. Because the way the cache works is that it's only saving intensity in the raw frames that are greater than the threshold value that you're putting in. So fit grains, positional argument, we have to put the configuration file. So it was example config, and I haven't run this, but just in case I can say -F to, let's do -C. I don't think I've run this analysis, but this will see what it's doing now here. As it's starting, it says it's reading 480 frames of data and storing values greater than 15 degrees. Only takes about 10 seconds, which is pretty good, and it gives us a compressed data format. Now it's going to load those. It's going to extract the spots and do a fit. So say refit wasn't specified, estimate wasn't specified, so it's fitting a 1 grain. Process it pretty quickly, and let's see now what else exists. So notice there's this directory now that was just updated. Let's see, cd. Remember our analysis name. So notice what's in here now. There are, I had run this previously, that's why there are existing spots. It was a different analysis. But notice the things that were just written are these 4 files here. Right here. So the frame cache. So just notice this is in bytes. So I took what are those, 8 gigabytes worth of data. That's about 4 gigabytes worth of data, I think, and it collapses it using a pretty low threshold to 18 megabytes. So that frame cache can get carried around. It's a good way for compressing the data. You can actually call the option to cache frames based on the config file as an option from the command line without doing the grain fits. There's a spots with a 5-digit padded index on it file, .out file, a grains.out file, and then a log that basically echoes what we had to the screen. So the spots in the grain files have everything that we want in there. So if I open the grains file and I truncate long lines, it has a bunch. It's something you can load in Excel, but as a header here, has 21 columns. But if we look through, there'll be, after the header, there'll be a row for every orientation that we fit in that accepted orientations .dat file. So notice my completeness, I have 94% of the reflections that I'm looking for all the way out to the edge of the detector. Chi-squared is a normal type of chi-squared fit parameter. It gives you goodness of fit. Something that's 10 to the minus 4 is definitely good. The next 3 columns, the C1, 0, 1, and 2, are the orientation in an exponential map format. So what those 3 numbers represent is the unit vector, if the 2 invariants of the orientation of the crystal. If you think of the invariance of an orientation matrix, would be an angle and an axis. So the exponential map is just the axis as a unit vector scaled by the rotation angle, and so that gives you those 3 parameters. It's a very handy parameterization for orientations to use. Based on my detector calibration, these TVEC 0, 1, and 2, this is the center of mass coordinates in the lab frame, or sample frame rather, of the crystal, and those are in millimeters, so you can see it's something like 11 micron, 11, 12, and what, 4-ish microns for the center of mass of my 153 micron crystal. This was centered, so even without doing a more careful calibration using this Ruby itself, I'm getting reasonable results since I already know that this was a manually centered crystal. The next 6 columns, these V inverse, 0, 1, 2, and then these, this should be 3, 4, 5 instead of 4, 5, 6. But in the headers, these are the inverse stretch tensor components in the 6-vector notation that I use internally. The last 6 columns are actually strain tensor components, so it's a log of the stretch tensor, and you can see that they're 10 to the minus 4, 5, or 6 magnitude. So again, without doing a careful calibration of the system based on the actual Ruby itself, it's comforting to see that the strains are in the 10 to the minus 4 below range since it's a calibrant crystal. If I open the spots file, this has a bunch of columns too. Now notice there'll be one of these files for every row of the grains.out file. So for grain 0, that's the spots 0 file, which we're looking at. The ID going down here, the only thing to note with that file is in places where there's a negative 999, that's a reflection that it did not find any intensity on the image above background where it was looking for a predicted reflection. There's a couple of different failure cases encoded in negative ID numbers in this file, but you don't need to worry about that too much. The PID is the actual encodes the G vector type. So even if you have different HKLs that have the same D-spacing, you can tell them apart by this unique identifier here. They're non-sequential, it's just the order that they were generated in. Then next 3 columns are HKL. After that, the next 2 columns are the sum of all of the pixel intensities in the window that I used based on the config file around each spot. This would be for the second fit, so the tighter windows. And then the max intensity of any pixel inside that window. This column here at the max intensities is a good way to figure out pixels that are saturated. So 14E4 on the GE detector is a saturated pixel. By default, when it does the fit, it is set up right now to exclude saturated pixels automatically based on a threshold that you tell it. So I've told it in one of the detector files that 14,000 is the saturation threshold, so it doesn't use anything over 14,000. Next 6 columns are the predicted 2 theta, eta, omega, and then the measured 2 theta, eta, omega from the actual image files here. So you can see in places where there's predicted but no measured reflection, there's just nans in those columns for the measured values. And then last, you have, instead of 2 theta, eta, omega, you have measured x, y, and omega, and this is in terms of millimeters on the detector and the detector frame. These things are used in the fit often, and then the measured omega is just copied, so I can just easily take the last 3 columns and know I have everything I need to characterize a spot on the detector. So in a nutshell, that is how you do grain fits. And the same works whether or not you have a calibration pattern or you're fitting 1,000 grains at a time. There's just some tricks that we can discuss later about how you optimize things for many, many grains instead of just a handful of grains.